He is currently a gameplay programmer at Ubisoft Quebec studio, where he worked on Assassin's Creed Syndicate. Previously he was a lead programmer for such games like sci-fi first shooter Alien Rage and the mobile title I Must Run. He also created physics, collision and animation subsystems for indie game engine called Argon. Overall, he has 13 years of professional experience and 15 games published on his track so far. So, ladies and gentlemen, give a big warm welcome, Mr. Bartłomiej Waszak.
Hello everybody, thank you very much. So my presentation is about Assassin's Creed Syndicate. I will talk about basically general gameplay programming in the open world. So I'd like to first introduce a bit the game. So Assassin's Creed Syndicate, long description, historical action adventure game with open world gameplay. So platforms PS4, Xbox One and PC. It's the first time when Ubisoft Quebec is the leading studio for the game. Before it was always Ubisoft Montreal, but right now it was Ubisoft Quebec. And we had the help of 9 other Ubisoft studios. So at peak time, probably around 1,000 people working on the game. And the setting was 19th century Victorian era London. And really for the first time, we had really a lot of dynamic objects in the game. We have massive simulation of the vehicles in the game, carriages, trains and boats. So it was really a huge move from static environment to the dynamic environment. From the programming point of view, basically for the gameplay programmer, it's C++ and custom scripting language. I will talk a bit about it later. So I have some little video. This time we have 2 heroes, twins, Jacob and Evie Fry. So this is Jacob Fry approach. So some driving across the streets of London. A bit crazy driving.
Impeccable time.
So on the top of the train, hijacking a carriage from the backside. And some fight on the top of the train. Yeah, so this is Jacob Fry approach, and we have the second hero.
Lots of guards.
A sister, Evie
Predictable
Fry.
patrol routes. Thorn may already be inside.
So this is also a new feature, rope launcher. You can travel more easily across the buildings. So Evie Fry is more for a more sneaky approach in the game. So you can really choose a lot of different ways to
Thought you'd want to speak with her.
Welcome, Miss Fry. Do you care to tell me where the shroud is?
So little nice cinematic at the end.
As you wish. I shall find it without your help. And then I'll strangle you with it. Watch her closely.
So this is a sister. So I will give you some overview of the presentation. So I will talk about gameplay programming, but I will give more focus on vehicles, new vehicle system. So I will give you some introduction to our object model and the whole world structure. I will present how vehicles are part of the game world. I will talk about carriages and trains. I will give you some info about how we work, how we cooperate with designers, so how designers can control behaviors from the data-driven approach. I will talk about state machines, like the main thing for gameplay programming, how to build and control logic for the game. I will try to introduce a bit, it's a huge topic, but I will try to introduce how we are working with animation tool and how we build animation system, how we control animations. And shortly about event-driven gameplay logic, multi-threading. And at the end I will give you some example for gameplay feature, which it will be taken from the trains, some feature for the train gameplay, which involves probably a lot of other parts of the whole presentation. So starting with object model and world structure. Very shortly, what I mean about entity, it's our main object represented in the world. So for me, entity is just position and rotation, some flags and components. Components are some configurable behaviors. So entities for me is like character, horse, street lamp, train, wagon. And components are like visual for rendering, rigid body component for physics, behavior or AI component, skeleton component for animations. And world structure, basically the world is collection of entities, but additionally world is also a single object with some additional world components, in the same way like entity and components of the entity. So those components, world components, they serve as managers for some gameplay subsystems. And examples of world components, like railway system component to control all the trains in the game, carriage manager to control all the carriages, river system component to control all the boats. So this is like examples from the vehicle's point of view. And very important part of working with a gameplay in open world game is the loading grid. Because we cannot have all the entities loaded all the time in the memory. So we need to control in some way which entities, which objects should be loaded at particular moment in time. So here is an example. This is some part of map of London. And it's a top-down view. And this is how it looks with loading grid. And from the engine point of view, whatever grid are very near the player, those are the grids that should be loaded right now. And engine manages loading like meshes, like collisions, like navigation meshes. This is like more the job on the engine side. But also we have some work to do on the game side. So for example, patching, dynamic patching for nav meshes somewhere around the vehicles. This is the job that needs to be done on the game side. And basically, from the gameplay programming, it's quite easy to manage and to access the world and loading grid. So we just ask current world with loading advisor, and we call some method from loading advisor to check if current cell in the loading grid is currently loaded at certain world position. So this is fairly easy. Based on that information, basically we can build all the gameplay logic and try to understand if currently something is happening on the loading grid, the cell is loaded or unloaded, and we need to do something special there. For example, vehicle is still there. Vehicles are managed by completely separated systems, so we need to be aware about it. So right now, how vehicles are part of this game world. So carriages. So carriage, from our point of view, is built from at least 3 entities, 3 game objects. So how it looks. It's one entity for the chassis, so it's like the main body for the carriage. We have another entity for the carriage tractor, which is just visual representation for all the, it's not the visual, it's the representation, physical representation for the horses, which are visual part of this. And we have at least one entity for the horse. So we can have for one carriage at least 3 or 4 entities. And why it is like that? Mostly because carriage physics. From the physics engine point of view, there is a strong relation that one entity is one dynamic object. And for carriages, we need at least 2 dynamic objects. We have one dynamic object for the chassis, so for the main body, and we have another dynamic body for the front horses, for the tractor. So tractor has no visual representation, but is simulated physically. and horses on the other side. They have no physical simulation, but they are represented in visual way. And thanks to that, we can create very easily physical constraint to model the hitch, so connection between the chassis and the tractor. So this is how it looks from the physics point of view, and it has direct consequence for the way how we design from the entity point of view, so from the game objects point of view. And it created a bit of problems in our code design, because a lot of problems was, is it carriage-centric or entity-centric? Because all the previous Assassin's Creed, they were extremely entity-centric. So it was because one character, one assassin is just one entity. So everything was, all the code for sounds, for special effects, for behaviors, everything was always entity-centric. And right now, when we had to move to carriages where we have at least 3 or 4 entities connected together in some way, it was a bit of mess. So we ended up with a lot of redirections in the code, and we need to decide which code needs to handle what part. So tractor code, chassis code, or horse code. We had a lot of things, a lot of redirections between all the entities to handle all the cases. It has one main consequence also for multi-threading. I will talk about it later. So right now, how it looks, how London was built, 19th century London. So as we can see on the old views of London, it was just full of carriages. So one of the main challenges in building the feeling of 19th century London was just to fill the streets with carriages. So this is how it looks in our game. So we need to take care not only about the short distance view, but also about long distance view when we had a lot of carriages in the distance. And in fact, a lot of work was spent to prepare this kind of behaviors. And one of the main challenges was the traffic spawning, because we have a lot of carriages around, and we need to handle spawning and despawning. And spawning in the game, basically, it has really high cost. And instead of spawning, despawning, we were using pool of reusable entities. So in fact, we were not spawning, despawning entities. We were just using very small pool of carriages, which are real entities, real game objects in the game, around 20 carriages. And instead of spawning, despawning, we're just reinitializing all the gameplay logic to keep the engine part not busy with spawning and despawning, but just to try on the game side, on the gameplay logic, try to do what we really need to do, and nothing more. So one of the things also important, we're reinitializing only once per frame to keep everything at minimum, and all the requests were processed based on the distance from the camera and some additional priorities. And thanks to this kind of spawning methods, we were able to simulate internally 512 objects for all the carriages around the player, but only 20 of them were real game objects entities with all the effects, sounds, all the logic behaviors, and all the dynamic or kinematic physics. And all the others were just extremely lightweight visual objects. Everything you see in the distance is not real game object, not real entity, but just extremely cheap visual object managed by the carriage manager. And also for carriages which are real entities, most of them were dynamic physics. So we were simulating really all the collisions between. And some of them were just animated objects, just kinematic physics. So this is the way how we were filling the London with carriages. Now I will talk a bit about trains. So this is how the trains looks in the game. On the right side we have a bit of physics for the trains. So the coupling chain and bumpers, how it works physically, with some additional little debugging info. And railway system, how it looks, how we build it. So this is the top-down view of some part of the railway system in London. And from our point of view, from logic, programming, gameplay point of view, this is the data part. So every line, every railway line is built as a collection of Bezier curves. So all these red or white lines, all of this, it's just Bezier curves connected at the turnouts. So all the blue points are the turnouts, so connections, and we can have multiple inputs and outputs. So the train can choose which way he wants to go. And additionally, we have some control points somewhere along the line. All those little green points. For example, to change the velocity of the train, or to play some additional effects, or play some sound. Whenever a locomotive or any other wagon is passing this control point, we can trigger some additional action. And how the trains, as the train were built. Every wagon was just the game object, train entity. But we were using a lot of sub-entities. As we can see in the background, this is the hideout for the player. It's really very complicated. Most of the objects are just part of the main mesh, but some of them were separated entities, like lamps or some additional physically simulated little objects. And we're using also a lot of parenting mechanism. And it was quite costly to update the whole physics hierarchy, because also trains were always in motion, so we had to update a lot. So we were cheating a bit. So we were not updating all the time. We were updating less frequently based on the distance from the camera, but also to make the movement still smooth. So we are moving only visuals, not the physics part, but only visuals with some predicted velocity. And now shortly about train physics. So we created custom physically based simulator. So this is taken from Wikipedia, so it's how the wagon connections looks right now. But it's almost the same as it was 100 years ago. So we have coupling chain and some bumpers. This is how it looks in our game. So instead of having all the wagons connected strongly together and not moving between, we created movable coupling chain which drives the movement for all wagons. So we need to test collisions between all the wagons. All the bumpers were working on that all the time. And we had some custom constraint solver for coupling chain. So basically it was very custom solution for the trains, but we were able to create some really nice behaviors whenever train was going to the full stop. All the wagons from the behind were hitting front wagons, so we had a lot of nice momentum transfers. Also the same for the startup for the train. So this is how we did trains in Assassin's Creed. And now shortly about our cooperation with the designers as gameplay programmers. And I won't talk a lot about it, but I want to talk just about one thing. This is like short description how it looks in general. So designers, they can control behaviors directly from the world editor. So we can create entities, all the data offline, and load them into the world, or just change parameters live during the game runtime to change and to test the behavior. And from the programming point of view, it looks very simple. We just have some variable, some parameter in editor, so just speed. Directly we have variable in the code, and we have some directly created methods to change the value of the parameter. But we find out that to create some more advanced behaviors, we need something more than simple linear dependencies. So simple parameters sometimes are not enough. And we use a lot of curves to control some behaviors. So instead of linear coefficients, we are using curves. And we use it a lot to control the handling for the carriage, how we transfer the controls from the gamepad inputs to the behavior of the vehicle. But we also use it for such things like the hit points, the damages for carriages. And how it looks from my point of view. So on the left we have just simple linear dependencies. So we convert collision amount taken from physics to some damage points for the carriage health. So it's very simple, but in fact it gives designers really little control. And on the right is the curve that the designer can draw inside the editor, so he can control directly what he needs. For example, for really small amount of collisions, he doesn't want really a lot of damage taken from the half of the carriage, so he can draw really a low line. But then, when the collision is really high, he wants to give really more penalty to the carriage, to the player and to the carriage halves, so he can draw it as he wants. So it really improved the iteration time and cooperation between the designers and programmers, because it wasn't like whenever designers wanted something new, he had to come to the programmer, ask for a new limit or new scale factor or whatever. He just could draw it probably directly in the editor. So right now a bit about state machines. What I mean about state machine is basically it's a very simple concept. Probably every game is using state machines in that way or other. Also for us, when working on Assassin's Creed, it's a basic building block for gameplay and AI logic. And we have internal scripting language to support directly state machines. And for example, every human and every character in the game has one state machine. Every carriage has a state machine. Every horse has a state machine. And gameplay programming on Assassin's Creed means you will work anyway a lot with state machines to control transitions, to control behaviors, what's happening in particular state, how to change states. You need to create hierarchies of these substates. It means really probably 50% of your time you will spend in some way working with state machines. And basic state machine structure. States have constructor, destructor, enter, exit methods. And they, as I said, they can build some hierarchies, so we have some substates. And one really nice thing in state machines in Assassin's Creed is that we could have exclusive states and additive states. And what I mean about it is that state machine is always in one of the exclusive states and maybe in one or more additive states. So as an example, how horse state machine looks. Almost all the states. So all of those states are exclusive states. So horse is always only in one of those states. So we have at the top level alive and dead. Then inside of the life hitched, unhitched. Then we have default, pending, deletion, and healthy dying in both unhitched and hitched default. But we have also some additional states, additive states, audio and effects and animations quality, and those states are to control audio and effects and some level of detail, and all of those additional states are active all the time. Doesn't matter what's happening on the left side. But still inside of the audio and effects, we have some additional exclusive states, active or inactive audio. And how example flow in horse state machine looks. So on kill event, is coming from the outside, and we need to handle it in some way. So we have 3 states which are supporting on-kill events. So default healthy, unhitched healthy, audio and effects, active audio. And only red states are active. So in default healthy, on-kill is triggering transition to the dying state, and active audio is triggering transition to the inactive audio. But healthy on-kill in unhitched state, the gray arrow, is not activated because it's not active state. So this is example how the flow in the state machine and how active states look in the state machine. And here's an example for carriage state machine. So kind of similar for the as we have for the horse. So we have also active and inactive state, detached, crashing, hitched substates to manage all the main basically behaviors and main logic states for the carriage. We have some additional, but on the inside of the active state, we have some additional additive states. So ownership and driver to control who is actually driving. Is it AI? Is it a player? Or there are no drivers? Or what's the ownership? Which system is trying to take ownership of the carriage? And we have this time we have a collection of additive states. So those states on the right are always active to manage, again, some animations for passengers, some special effects, some impulses, rooftop ejection, which is to trigger ejection of the character whenever it is hitting some big collision, and additional state to control damage, destruction basically of the carriage. So this is how carriage state machine looks like. And right now I will talk about animation system and how we manage communication between programmers and animators. And to do it, I need to start with real-time control parameters. What I mean about it is that it's basically data-driven control over the system with some set of very simple parameters. And those parameters are using very basic types like float, integer, or enumeration, or vector. Examples like velocity, acceleration, some emotional state, impact direction. And we use this kind of real-time control parameters to control all the animation system, all the audio system, and all the special effects system. And basically, why we are doing it this way, it's fully data-driven control, and it makes way much less coupled all the subsystems between each other. We create, based on that, very simple interfaces, which are way much more easier to control. And what's probably the most important part of that is that it is way much more easier to understand by non-programmers. Probably every animator has the meaning for the acceleration or velocity or emotional state. So it improves a lot cooperation between programmers and animators. And one of the examples of real-time control parameter, velocity, it turns out that it's not so easy to do it in Assassin's Creed game, because we have multiple behaviors for entities in the open world game. We can control entity for dynamically through the physics, from the animations or some procedural stuff. We have a lot of different managers who can control carriage. And it's not so easy to do it for the velocity to be smooth enough, for example, for the sound control or some animation blending. And instead of using a lot of branching and asking every manager what's the velocity of this object, what I need to do to get it, to do it correctly, we just did completely separated approach, And we are computing velocity totally externally, independent on the source of movement. So we are just asking entity for its actual position, and we're calculating velocity totally externally, just looking for the changes in the position. So it will work even for any unknown future. Whatever new manager to control carriage will be created, this solution will work anyway. So this is very general overview, but how we did it. We just keep positions for the carriage for some n last frames, like 8 last frames, and we just use directly physical equations to always to keep velocity updated. So we just calculate the total distance in last frames, and we just divide by the total time of the past frames. Also, it gives us very natural way to have velocity very smooth, because, for example, we had a lot of problems with the sound, the audio designers who were always complaining that velocity is not smooth enough whenever we are trying to take it directly from any other source. So it was also a very natural way to smooth out the value. And here is the example. We created also some additional debugging info. There are little rectangles on the left side, and to track velocity, acceleration, and the third derivative of position, jerk. So this is another way that we were able to, in the same way, calculate acceleration and jerk, values which are many times not directly given by any other manager. So, for example, the lowest one here, the jerk one, is always changing only whenever acceleration is changing. And for example, based on that, we can control some blending of the animations for the passengers, or do anything what we want with the horse.
Walk on, girl.
And in fact, creating this kind of debugging tool, it helps a lot to check, and we also were able to fix any other problems with the movement of the carriage, which we're able to track just checking velocity of the carriage or acceleration. So, from general point of view, animation system, we can think about it in terms of the layers. So the first layer is the set of real-time control parameters, and this is the work for the programmers. We just create good calculations for such things like velocity, like acceleration, like impact direction, and then the work for animators start. So they, based on the set of parameters, they create some state machines internally in the animation tool, totally externally, totally in the data, totally externally to the work of programmers, and they output final transformations for the bones back to the engine, to the game, and then is again the work for programmers. So we can play put some I key or whatever we want to do with the final pose of the character or horse or another animated object. And there's a very common pattern in Assassin's Creed, which is the coupling between the behavior code, which I mean state machine code, and some communication with animation tool with animators. So for example, we have some alive state, we have some method to enter the state and to exit the state, we have some body for this state, and whenever we are entering or exiting this state, we are sending proper data to the animation tool. So we are just, and it's that easy. So we just change the general state to the alive whenever we enter alive state, and whenever we exit, we just switch back to the default state. And basically, this is the way of communication with animators. And horse animations, how it looks in practice. So it was quite specific because most of the objects they could be animation driven or physics driven. For example, in Assassin's Creed, main character is animation driven. So all the displacement, physical displacement for the collision is always taken from the animation. But horses, basically, they are not physically driven. Only the whole tractor are physically driven. So horses are moved with the physics. It's not animation. Animation is trying to following the physics. So we had to scale the playback of the animation to keep the current physical speed. And we are also blending different animations, walk, trot, and gallop, depending on the speed. And additionally, we have some heat reactions. They were just simple additive animations on top of the basic movement animations. So right now, a bit about event-driven gameplay logic. So how it looks in Assassin's Creed. So basically, this is a way to, for us, it's the way how to communicate, how to make communication between sometimes totally unrelated entities, game objects in the world. So one entity creates a new event, and an event can be sent to one of the channels. So we choose one of the channels, and then we have some other entities to listen to this particular channel, and they will always receive whatever new event is sent to the channel. So this is one of the patterns in Assassin's Creed to control the events flow. And the second pattern is just directly creating an event and sending an event directly just to one entity in the world. An example of the creation of the event is basically very simple. We just create a new objects of particular class, for example, my event explosion, just to create some explosion. We just set some data and we call function to send this event to the channel I want. And receiving the event is also quite simple. So upon the receiving of the event, we just have some method called, and it can be immediately or deferred in some part of the frame, probably somewhere at the end, to handle all the events sent in the game. And examples of the events created in the game. So for example, destructible hit. So it's whenever a carriage is hitting a lamp or a tree or another object, we always create some event that could be handled by any other object that wants to handle in some way or do some specific thing anytime in the future. We have ramming events, so whenever two carriages are hitting each other and triggering special input. Or some very specific event from the physics, whenever a carriage tractor, so invisible entity only for the physics of horses, is colliding with characters, or the physics engine is triggering this kind of event handled somewhere in the game code. So right now, very shortly about multi-threading. Probably there could be a totally separated presentation about all the multi-threading in Assassin's Creed. This is just very short description, very specific also for the vehicles. So all the entities are always, we have update always in parallel for all the entities, but there are some restrictions for that. And here is the screenshot of our internal tool, optimization tool. And we have here two threads. And there is one carriage, just all the tasks for the one carriage, for the update of the logic. And there is second carriage on another thread. So both carriages, without any synchronization, they cannot call whatever method between, because it will always create any kind of weird problems. But to make all the things easier, we keep single-threaded update for the related entities. So whatever horse is attached to the carriage, or whatever human is already standing on top of the carriage, we keep always linear update on the same thread. So for example, horses are updated also in parallel between each other on different threads, but they are always updated after related carriage. So horse A always after carriage A, horse B always after carriage B. And it's the same for humans. So every character which is interacting in any way with the carriage, entering a carriage or standing on top of the carriage, also is always updated after related objects. So in very general, because it's a very huge topic, but very general, we don't need to use any kind of synchronization, multi-threading synchronization between related objects, but we need to do it whenever we want to cross this boundary. So whenever we need to communicate in some way between totally unrelated carriages, we need to do some kind of synchronization. So at the end, I want to present one of the features from the trains. So this is the coupling of the train wagons. So basically it's on the input. Whenever player is approaching it, it shows some UI stuff. Player needs to keep pushing the button, and then the wagons are detached. So how it looks from the gameplay code, from the gameplay programming point of view. So first we need to detect coupling chain in the proximity of the player, and we wait for a button. And whenever player he wants to start the interaction somewhere around the connection of the coupling chain, there is a new transition to some new state in human state machine, something like the coupling train wagons. So here is the part where the real logic starts, and we are going somewhere to substate like decoupling, and this new state is starting communication with animation tools. So it sends new RTCP, and animation tool, animation graph is starting new animation. At the beginning of this animation, because the player can start interactions anywhere along around the coupling chain, we need to adjust the player's position and orient it at the desired place, somewhere in front of the coupling chain. And it's the very short time at the beginning of animation, and it's controlled basically directly by the animator, how it works and when it starts and when it needs to be finished. And also during the playback of the animation, of course, we trigger some audio and special effects, so it's directly taken from the animation. And finally, somewhere very near the end of the animation, we have specific markup in the animation timeline to trigger the callback back to the code. So we call some decouple method in the specific code for wagon. This decouple method is informing the physics. Okay, right now we need to stop simulation between both wagons. We need to detach the coupling chain. We need to start physics for slow, free, just fall of the chain. And we are informing manager, high-level manager, world manager. But right now, we have two trains, and railway system component needs to split one train into two groups, totally separated groups. And physics is, of course, simulating still right now two trains, and one behind is slowing down. And at the same time, new event is broadcasted. So wagon detach event, whoever wants to handle this event and do some special things, trigger some special effect or some UI stuff, it can be done just directly handling this broadcasted event. So in this one relatively simple feature, we need to touch like state machines, animation tool, high-level managers, and all the some event-driven gameplay logic. So that's it on my side. If you, I want to give the special thanks to my team. I presented basically the work of the whole team. So vehicles team, we were like 5, 6, depending on the time, or even 7 programmers. And I want to thank Leszek Godlewski for the help of helping me with the final presentation. So thank you very much. If you have any questions, feel free. Yeah.
Hello. How
Hey.
did you solve problems with slope terrain and the carriages? Visually, at least.
Yeah, it was depending on the type of the physics. If you had dynamic physics, it was just fully simulated, so it was always adjusting to the terrain. For the kinematic physics, as far as I remember, we were more just casting ray, just one ray down for one carriage, and we were just adjusting the carriage according to the normal of the heat. So it wasn't so easy. I remember we had a lot of problems with that, especially with wrong data for the terrain and all the, especially bridges and all the connections between the flat terrain and the beginning of the bridge. But if I remember correctly, it was just one ray cast and just align with the direction of the normal.
One more. And the horse's legs?
Horse's legs, I wasn't talking about it, special Aiki.
Okay.
So
Thanks.
it was really a lot of work.
I can imagine.
Yeah, but finally it was a combination, horses were combination of really a lot of work on animation side to really properly align the animation playback speed to current physics speed, and different animations like walking, gallop, trot, to blend correctly between them. Of course, also some startups and breaks. It was also a lot of tricky things. But on top of that, there was really special Aiki made for that. I don't know exactly the details, but basically combination of all those things were working finally, really giving really good results.
Thanks.
Thank you.
So I want to ask about the event channels you were talking about. So basically the question is it like a simple approach of one channel per type of event, or did you have some finer grouping or classification of those?
You mean, we had several channels to, if you, for example, we had like sound channel to send all the sounds, sound-related events to one channel, and whoever and other game objects wanted to support in some way sounds or do some specific things, he had to listen to the sound channel.
So it was basically grouped by subsystem, and then the object got all the events from the subsystem and decided if it want to handle it or not.
Exactly
Okay.
like that.
Thanks.
No problem.
I also wanted to ask about this event system, and I got 2 questions. First, were those events used to communicate communication between entities, or also between the components?
As far as I remember, to be honest, I think it was mostly for the entities. But you could support also listening and sending the events also for some other objects. But for the mostly, I would say 90% of the events were always entity-based. So it was kind of more high-level communication.
Okay, and the second question is, was it useful to have these two methods of sending events, one directly and the second with the usage of channels?
Yes. It's hard to say for me about statistics. Most of the events, if I remember correctly, were sent directly to the entity. So we always knew which entity we want to send, but then entity was deciding what to do next when receiving the event. But also there were some specific channels like sound channel. I remember there were also some animation channels. So there were really way much more specific things. And you could, like, in proximity of the entity, so everybody could check what's happening around. So you could also send it directly to the channel and don't think about who will receive it.
Okay, thank you.
No problem.
I have a question in terms of scheduling of the event handling. I mean, does handling of the event occur in the same frame, or is it scheduled for the next one? Because I can imagine that this is giving both benefits and problems in terms of multi-threading.
Yes.
So
exactly.
I wonder.
Yes, exactly. If I remember correctly, most of the events, even sending event directly to the other entity, it was always registered somewhere, and all the events were always sent at the specific moment in the task graph, multi-threading task graph, that we were sure that there are no other tasks or other work done which could be related to the work done for this entity. So we are sure that nothing else on any other thread is happening. We are just supporting the events. But also I need to say that at some point we had problems that because of that basically we were stopping the CPU and we're only supporting to receive the events. We had to be sure that really there is very little work done there. So for example, just remember that you receive the event, but then do some special work in another frame during your multi-threading update. So the events were really a kind of tricky thing to do, but overall I think it was working quite well. You just had to remember that this is a point where the game stops and you are just receiving events. Do it very quickly.
So it looks like there is a lot of gameplay data. I mean, only gameplay, not animation, but those curves for animation and stuff like that. So did you process them any way in the build times to have like data-driven approach when you...
Yes, there's a lot of processing of the data. I don't know all the details, but to process all the data, it takes a lot of time. So there's a lot of additional tools to help gameplay programmers. There's also a lot of separated, like the chains of processing the data between runtime editor and the final engine build. They're like everywhere. But as you asked for the curves, always you think about limiting the amount of data. So curves were also built using some Bezier lines. Yeah. So in fact, it looks like it's way much more complicated, but in fact, because of you can smooth and you can change the shape of Bezier curve very easily. In fact, you need to store really way much less data that you can think about at the beginning.
Okay, thank you.
Any more questions?
Hey, I remember you mentioning something about making the objects only visual depending upon the distance from the camera.
Yeah.
Speaking about visual, did you also use some sort of animation LOD system to reduce the details in the animations also?
Yes, as far as I remember, we can control we can call it quality, but in fact it's a kind of level of detail for the animation playback. And for example, for horses, we were using lower level of detail for animation playback depending on the distance from the camera. And what it means is that in very simple implementation is just that you drop at some when you have skeleton and you have the hierarchy of bones, you just drop at some point at some level of deepness, just you don't update all the little bones after some level. So like you don't update hands for the character or fingers or whatever. It was very simple implementation. I guess, I don't know the details right now, but I guess there is a lot of other work which can be dropped depending on the distance from the camera, and for sure we're using that for the horses. As you asked also about simple visual objects, it was made totally, as far as I remember, in very far distance, they were not animated at all. So just very little objects somewhere in the far distance.
Okay, thank you.
Anyone else? We still have time, so yep.
Hi.
Hey.
You mentioned about loading grid, and then you mentioned about the levels of the object. I mean that the closest object had rigid bodies and the far ones was just only renderers.
Mm-hmm.
And also you mentioned about pulling the objects. So it's not visible for the player, then you move to the other part of the city and you have the still 25 pull of the carrots, horses I mean.
Yeah, carriages.
Yeah, okay, but what about trains? Because as I imagine the grid of loading, you are unloading some part of cities, and I mean,
yes.
What about trains? Because the train should be at, for example, 12 p.m. in this point of city. Does game manager still works with the objects which are not rendered?
Mm-hmm. With trains, yeah, it's a good question. With trains, we had a lot of such problems, and it's completely different system. And basically, it's very player-centric approach. So we spawn the train whenever player is approaching the station, and we despawn it whenever it is quite far away from the player. So because at the beginning we tried to create a kind of very complicated London scheduling of the trains, but we ended up that the player really never see the train because it's all or far away or just nothing is happening around the player. And if we wish to do this kind of approach, probably we had to have like 50 trains in London running all the time, probably. So we didn't have time to do it at that point. We had to do probably something specific for that. We still had a visual level of detail, but it wasn't enough because trains were so complicated in terms of entities, hierarchies, and all the little like different visual rendering settings. I know I'm not the rendering guy, but I know that we had to create some sub-entities with some different settings for the rendering. So we had really way much more complicated physical hierarchy to update it. And because trains were always in motion, we had to always update all the matrices for the sub-entities and send it to physics engine and do it every frame. So it was very costly, and we had to do it less frequently depending on the distance from the camera, but still we had to limit amount of trains and spawn them only related to the player position. So whenever you're playing Assassin's Creed Syndicate, we are a kind of cheating to give the player just the feeling of that the London is full of trains, where in fact it isn't.
So I can back to the same place 2 times in 2 games and at the same time schedule, and I can get different results, yes?
Most likely,
Okay.
but there are some specific types of the trains which are always loaded, like hideout for the player, which is a kind of place where you can always go back and trigger some other missions. It's always running in London, and you can always approach this train probably with some really designed schedule. There are also some activities like hijacking the train, so you can steal some cargo from the trains, and they were also running with some specific schedule, and you could do this kind of activity whenever you want. So I know that they are always running with some specific scheduling, so probably you would approach those trains at the same time. But I know that not gameplay imported trains, like some passenger trains running around London, probably not. Probably they are running just randomly around you.
Thank you.
Thank you.
Do you have any entities in the game that you have to maintain state machines for them, even if they are outside players' view or interest? All the time, I mean?
Yeah, I understand. I can't remember any right now, to be honest. So it's always a kind of reinitialization for whenever we are approaching the object with state machine and it's closer to the player, we are just reinitializing it. I don't remember any kind of logic that it's extremely persistent. This kind of logic is somewhere at the top level of world component. So really some internal data like position, velocity, or some state, but really in a kind of simple way. So it's externally, and whenever this manager receives information, player is approaching this kind of object, this manager is reinitializing real entity again with the logic. So this is the way it's most of the times done. I don't remember any kind of extremely persistent state machine except for the player, most likely.
Thank you.
Thank you.
Anyone else? Feel free to ask. Yep.
Hi.
Hey.
I got a question about traffic.
Yes.
I'm wondering how you are handling traffic, because obviously, city is a living organism with a lot of bottlenecks and stuff like that, and obviously there's less traffic in the suburbs, and etc., etc. And so I'm wondering if you are keeping like any sort of heat map of the traffic in the game,
yes.
or how you are handling it.
Yes, exactly. This is a kind of I wasn't talking about it, but like we have a map of London. So we can paint some regions on the map. It's inside the tool. So designer can paint some regions on the map and decide whatever it should happen there, like more traffic, less traffic, or some different parameters for the traffic depending on the other situations. So this was a kind of approach. I also remember that it was very tricky to it was very hard problem to support that whenever you were just walking like in previous Assassin's Creed, just around the street, you always wanted to enter the carriage and you always had to have a lot of carriages around you. But when you started to drive, you wish to have less carriages because you couldn't drive around because you were always hitting other carriages. So we had to do a kind of dynamic changes, dynamic solution to change the density of the traffic depending on the player situation. So most of the time it was the most dense traffic around the player when he's walking, and really just less dense traffic whenever player is driving, because it was very frustrating not able to drive through the streets. Even if it is, you can imagine that it would be more interesting, but in fact it was more frustrated for the player. And of course, it was a kind of additional factor, depending on the priorities, whatever was happening in the game, and what was more important, to support the region-based density or the player-centric density. So
Thanks.
there was a lot of work done on this part, for sure.
Okay, thanks.
Thank you.
Anyone else? That probably covers it.
Thank you very much.
Thank you very much.